Hello, my name is Sandrine, and in this video, I will be presenting to you my individual project for the MSc Computing Science program at Imperial College London. So my individual project is entitled Mining Argumentative Abstractions from Deep Convolutional Neural Networks. And just to provide you with a little bit of context, so this project is part of a wider effort in the field of AI to make AI models, including neural networks, which can be considered black box models, more transparent by providing explanations of their output. More specifically, the project focuses on deep CNNs, convolutional neural networks, and more specifically, those that are used for text classification. Now, why this focus? Well, first of all, text classification regroups a number of applications, such as sentiment analysis, topic classification, and even natural language inference, all of which are of prime importance in natural language processing. And secondly, CNNs are one of the most widely used architectures in NLP, alongside recurrent neural networks and transformers. As an illustration of this, if you go on the Papers with Code website and look at the state-of-the-art models for natural language processing, a number of them include a CNN component. Now, before I go on to explain how to derive explanations for CNN's predictions, I will quickly recap what a CNN is and a deep CNN more specifically. So a deep CNN, like any deep neural network, is composed of different layers. So namely an input layer, which contains the textual data used as input for the model, pre-processed. A number of hidden layers, as well as an output layer, which contains the final prediction. Now, what characterizes deep CNNs is that a number of their hidden layers will be convolutional layers. So what is a convolutional layer? Well, the fundamental principle of a convolutional layer is that it contains a fixed size matrix called a filter, which slides over some input, and the input values over which the matrix spans are multiplied element-wise with the values of the matrix, and the bias, if used, is then added to the product, where the bias is simply a constant. The result then constitutes the input into the next layer, and the bias and values inside the matrix are the trainable parameters. Importantly, convolutional layers typically have several filters, which means that several matrices with the same size are applied to the same input, each producing a separate output. Convolutional layers in CNNs are typically used in conjunction with pooling layers. These layers also use a sliding window of a given size, which either calculates the average of the inputs it spans over, in which case it's called average pooling, or selects the inputs with the greatest value, in which case it's called max pooling. So now that we know how a CNN works, how do we get an explanation with respect to its predictions? Well, the strategy proposed in this project is to extract from the CNNs an argumentation framework, where an argumentation framework is simply a nodes and edges data structure, where each node is an argument and each edge is a relation between two arguments, such as an attack relation or a support relation. And the entire data structure as a whole therefore represents the models in a debate with respect to its final decision. And the idea is that once we have extracted this argumentation framework, then we can use it to generate explanations. So how do we extract an argumentation framework? Well, the first thing that you need to do is that having a trained network, you need to interpret every neuron in this trained network as a semantically meaningful argument. So assuming our model operates over input that has been pre-processed on the word level, we can say that the neurons in the input layer refer to words. Then, because convolutional layers can be seen to aggregate input and assign a new value to this aggregate, we can interpret convolutions over input neurons to refer to groups of words, such as, in other words, n-grams, where n is the size of the convolutional window. Similarly, convolutions over convolutions therefore refer to, can be understood as referring to groups of words, in other words, groups of n-grams, etc., etc. So once we've interpreted those neurons in this manner, we need to perform a forward pass on this trained network and record the output at every layer generated during this forward pass. Once we've done this, we can use the recorded values to calculate the strengths of the arguments that we've identified. So how do we calculate the strength of arguments? Well, we can use methods that are called attribution methods to do this. So an attribution method is a method to quantify the contribution of individual neurons in a network to the final prediction. So the attribution method that we have been using in this project specifically is called layer-wise relevance propagation. And the idea is that it backpropagates the final output of the network to previous layers using a given set of rules. So once we have followed this procedure, we should obtain an argumentation framework, which could look something like this. So in this case, we have used a very, very simple CNN for illustration, which is composed of a single convolutional layer, which itself only contains 2 filters, and the size of the window in these filters is always 2. In other words, it aggregates over pairs of words to create n-grams. So once we have this argumentation framework, we can derive explanations in terms of words, in terms of n-grams, or in terms of filters in the convolutional layers by simply looking at the relevant arguments in the data structure. But what's really interesting with working with argumentation frameworks is that we are able to extract explanations from entire branches of the data structure. For instance, we might want to have an explanation of the final prediction in terms of a given n-gram, but we might want to dig deeper and for this specific n-gram, know exactly which words that compose it mostly contributed to this n-gram, in turn contributing to the final prediction. Similarly, we might want to have an explanation of the final prediction in terms of an n-gram, but then decompose this n-gram into the different filters that detected it. Now, I've been talking about filters and filter arguments inside this argumentation framework. For most people, this is not a very compelling concept, especially to people who have no prior knowledge about neural networks. So one solution to this problem is to actually combine these filter arguments with natural language concepts, which we have extracted from the training set, that is the data set on which the neural network was trained on, and see which concepts each filter mostly detects. This allows us to provide an identity to each of these filters. So now I've described the theory of extracting argumentation frameworks and how to use them for explanations. But to make things more clear, I will now proceed to a demo in which I will show you how argumentation frameworks can be used with a user interface to provide compelling interactive explanations. So this UI is a simple web page from which we can get a random article extract. And then for this extract, get a prediction. So the model basically tries to classify this extract in terms of topics. So there are 4 possible topics, which is sports, world, business, and science and technology. Here we can see that the predicted class is sports. And under, the user has the possibility of having an explanation for this prediction. So for instance, clicking on Y, we can see the group of words that mostly contributed to the prediction sports. The user can ask for more groups of words to justify this classification. And for each group of words, the user can actually see the breakdown into the different words that compose the group of words. So for example, for the n-gram Toronto Raptors, we can see the breakdown between Toronto and Raptors and see Raptors mostly contribute to the prediction. Similarly, we can see exactly which filters detected this group of words. And thanks to the natural language concepts associated to these filters, we can get an idea of what kind of concepts these filters detect. For example, for Toronto Raptors, this n-gram was mostly detected by filter 17, which typically also detected in the training set the concepts rookie shortstop, Yankees outfielders, and Steelers linebacker. Once again, the user is able to ask the UI for more filters, as there are several filters that will have detected the same group of words. So that's one type of explanation, but maybe the user is more interested in counterfactual explanations. So an explanation as to why the extract was not classified as science and technology, for instance, or business or world. In this case, we can see that it's always the same n-gram, but for different examples, it could be different n-grams. And it gives us a more fine-grained understanding of the model. And just like with the other types of arguments, we can see the breakdown into the different words and the different filters that detected the group of words. And we can ask for more arguments. And then at the very bottom of the page, we can see each individual word that composes the extract and how each of them contributed to the prediction overall. So looking at this, we can see that the individual word that mostly contributed to the classification sports is Raptors. Clicking on this word, we can then see every n-gram the word belongs to, and just like before, we can see the word breakdown and the filter breakdown. So one note about the color code on this page, green refers to support, so it's words that have contributed positively to the prediction, and red refers to negative, so attack, negatively contributed to the prediction. So in summary, we can see that argumentation frameworks can be used to derive high quality explanations which draw connections between outputs from different layers of a CNN. Thank you very much for listening to this presentation. I hope you found it interesting.